Hello, AB Stats! Hope you guys are having a great day. Today I'm going to be going over the Chapter 5 review. So Chapter 5 is the first chapter of probability, about the basic probability rules, what to do when things are mutually exclusive, what it means to be independent events, and just how to calculate basic probability. So, number 1. Okay, you toss 3 coins. List all possible outcomes in the sample space. Okay, so you toss 3 coins. Your first coin, the option is head or tails. Right? The second coin, option is head or tails. Third coin, option is head or tails. And so your sample space is all of the possible outcomes you could possibly have in this sample space. So we could have head, 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 tail, head, tail, head, right? And we could go on. And so I'm going to list those out for you. Yeah, cool. Alright, so there are all my possibilities in this sample space. Okay? Alright, so number 2 says, using the results from problem number 1, what's the probability of getting exactly 2 tails? And so in which case you want to look at all of the possible options that I have. Whoops. That have 2 tails. Okay, so exactly 2 tails. Here, here, and here. So that's 3 out of 8 possibilities. And number 2 says at most 2 tails, which means we're okay with no tails. We're okay with, let's actually highlight those. We're okay with no tails. We're okay with 1 tail. And we're okay with 2 tails. So I could add up all the ones that have at most 2 tails, or I could find the only option that has more than that and subtract it from 1, right, and use the complement rule. But you get the same answer either way, 7 out of 8. Alright, 3. In a single pick, so one single card from a normal deck of cards, what's the probability of getting a heart or a jack? Okay, so that means if I get a heart, I'm happy. If I get a jack, I'm happy. If I get the jack of hearts, I'm also happy. Okay, so these 2 events are not mutually exclusive, right? Because I do also have a jack of hearts. And so if I use my, my probability of A or B, right, that's the probability of getting, so the probability of getting a heart or a jack. Let's actually write that in because I think it makes more sense if we use the actual context. You want to look at the probability of getting a heart plus the probability of getting a jack. And then the problem is, since there's an overlap, right, they're not mutually exclusive, you have to subtract out when both things are satisfied, because otherwise you're counting them twice. Okay, so then we would subtract the probability of getting a heart and a jack at the same time. Okay, probability of getting a heart in a normal deck of cards is 13 out of 52. Right, there's 13 hearts. There are 4 jacks, so 4 out of 52. And then I'm subtracting the probability of getting a heart and a jack. So there's only 1 card in the deck that is both a heart and a jack. So you're subtracting out 1 out of 52 for a grand total of 16 out of 52. Alright, number 4. Are the following pair of events mutually exclusive, yes or no? Alright, number 1, selecting a student enrolled in statistics and selecting a student enrolled in physics. Okay, now the question is, are there any students at Dawson who are taking both stats and physics? If there are any kids who are taking both, then they're not mutually exclusive. So the only way you would know, well, I mean, you'd have to actually look at everybody's schedules, right, and see if there's somebody taking both. I imagine yes, there are people taking both. So I would assume no for this case. Something that might be mutually exclusive is a student enrolled in Algebra 2 and a student enrolled in Algebra 2 Honors, right? Because you won't have somebody taking both classes at the same time. Okay, next problem. County elections. Okay, you have 6 Democrats, 5 that are women, which means 1 man, 8 Republicans, 3 are women, and 4 conservatives, 1 is a woman. Alright, so in order to solve the first question, what's the probability of selecting a male or a Democrat? We need to know the probability of selecting a male first. Okay, so probability of selecting a male. Well, we know that out of the 6, 14, 18 people, right, 5 are women of the Democrats, so that means there's 1 man there. 3 out of the 8 Republicans are women, so that means that 5 are men, and then of the conservatives, 3 are women. Sorry, 1 is a woman, 3 are men. Woo! Okay, so what that means is I have a total of 6, 9 out of 18 that are males. Okay, the probability of someone being a Democrat is 6 out of the total, so 6 out of 18. And so in order to get the probability of selecting a male or a Democrat, we need probability of male plus the probability of being a Democrat, and then subtract off the probability of them being both, because I don't want to double count. So probability of male and Democrat. So I have 9 out of 18 plus 6 out of 18 minus 1 out of 18. Okay, so you end up with 9 plus 6 is 15, minus 1 is 14, so I end up with 14 out of 18 for number 6. Alright, number 7. Probability of a fire occurring given an earthquake has occurred is 0.2. Alright, so we are given that an earthquake has occurred. So our 2 events that we need to kind of look at is fire and earthquake. Okay, so the probability of a fire given an earthquake is 0.2. The probability of an earthquake occurring alone is 0.005. Find the probability of a fire and an earthquake occurring at the same time. So we want to know the probability of fire and earthquake. This is what we're looking for. Alright, so this one's actually pretty straightforward because we have that formula on your stats worksheet, your stats packet, that says the probability of A given B is equal to the probability of A and B all over the probability of B, right? And so in this case, we have the probability of fire given earthquake, and we have the probability of an earthquake is our B, right? And so we know those 2 values. We know this one and we know this one. And so we just plug them in and solve for the probability of A and B. Pretty straightforward, okay? As long as you knew to use this formula. So I plug those in and I get probability of fire given earthquake is 0.2, and I want to multiply that by my probability of an earthquake, which is 0.0005, and that's the probability of fire and earthquake. So then you can simplify that and get your probability of fire and earthquake to be 0.001. Cool. All right. Next problem. Given the joint probability distribution below, determine the following. Probability B, probability of A and Z. Okay, blah, blah, right? So let's just double check this and make sure this whole, it should. It's a probability distribution, so it should all add up to 1. So if I add 0.04 plus 0.13 plus 0.14, add all of them up, they should end up adding up to 1. And probably a really good way to do this, because I have to like figure out what the other things are anyways, I'm going to add across my rows and my columns and just kind of see what totals I have. So like the total percentage of X happening, right, is 0.04 plus 0.10 plus 0.11, right, which is 0.25. So I just add that in here, 0.25. My total Y is 0.15 plus 0.25 plus 0.13, okay, which is going to end up being 53.53, and then the probability of Z is going to be 0.14 plus, so 0.22. And then if I want to find my total probability of A, that's going to be 0.27 plus 0.04 is 0.31. Probability of B occurring is 20.27. And the probability of C occurring is 3642.42. And then just check and make sure those totals add up to 1. 0.25 plus 0.53 plus 0.22 adds up to 1. 0.31 plus 0.27 plus 0.42 adds up to 1. Right, so we're good there. So total is 1. Right, so the question is, what's the probability of B occurring? Well, that's the probability of just getting B, which is 0.27. Okay, I'm going to zoom in a little bit here. Okay, so the probability of B is 0.27. The probability of A and Z occurring, right? So A being true and also Z being true is just this 0.14. Okay. The probability of B or Y, okay, so that is not this 0.15, because that's the probability of B and Y occurring at the same time, but I want the probability of B happening or the probability of Y happening. So that's your 0.27 plus your 0.53, but both of those counted the 0.15, so you have to subtract it out. So my total there is 0.27 plus 0.53 minus 0.15. Okay, and so then that adds up to 70, 80, 70, 65, 0.65. Okay, probability of not C is 1 minus the probability of C, so here's C, so we want 1 minus 0.42, so that's 0.58. Probability of A given X, so we know X is true, and we want to know the probability of A happening given that X is true. Well, that's going to be your probability of A and X happening divided by the probability of X happening, right? So that's that 0.04 divided by 0.25, right? You're given that X is true, so 25% of the time. And what percent of that is A occurring? So 0.04 divided by 0.25 is 0.16. So that would be E. So the next problem is asking for check for independence. Remember, there's two ways you can check for independence. The first is to check if A and B is equal to the probability of A times the probability of B. And the other option is that the probability of one given the other doesn't change the probability of the first thing happening, right? The probability of B given Z is still just the probability of B. Like, it doesn't change given the information of Z happening, right? So you can just calculate both of these, and if they're equal, they're independent. If they're not equal, not independent. If you do it the first way, you find that the probability of B times probability of Z is 0.0594, which is not the same thing as the probability of B and Z, so this is not independent. All right, last problem. So based on data from this just abstract of the United States, 12.5% of the general population are senior citizens. Only about 14% of the senior citizens get the flu each year, while 24% of the people who are under 65 years of age get the flu each year. Using F for flu, S for senior citizens, find the probability that a person selected at random is a senior citizen, given that they have the flu this year. Okay, so I like to, in this case, I think a tree diagram might be kind of nice. You have your initial situation, right, is that 12.5% of the general population are senior citizens. So I could, if I wanted to, do so seniors and the rest of the population, the general population. Let's call it G for the general pop. Okay, so we've got 12.5% of the general population are senior citizens, 0.125, which then means that 0.875, right, because that has to add up to 1, because we have senior citizens and non-senior citizens, or the general population. And then it says only about 14% of senior citizens get the flu each year. So 14% of the senior citizens get the flu. So I'm going to do a flu and no flu. So 14% of the senior citizens get flu, which means that 86% do not get the flu. And then it says 24% of the people under 65 get the flu. So from our general population, we have flu and no flu, and 24% and 76% for no flu. Okay. So then we can find the probability. So like this top trail, right, S and then F, right, if I multiply those all together, then I get the probability of a senior citizen getting the flu. So that's 0.125 times 0.14, and that is 0.0175. Okay, and then the second route, I have a senior citizen not getting the flu, then I have the general public getting the flu, and then I have general public not getting the flu. And for any of those probabilities, I just multiply them together. And so it's asking us that a person selected at random is a senior citizen, given that they get the flu this year. Aha, it's a given problem. Okay, so we didn't actually need to make a tree diagram, I think. But that's okay. I made one anyways, just so that you can kind of like see that situation, right? But really what we're trying to figure out is the probability of them being a senior citizen given that they got the flu. Okay, tree diagram might help. Let's just see what happens. All right, so the probability of the senior given that they got the flu. So using the formula in your packet, you could do, this is the probability that, so again, given your formula sheet, probability of senior given that you know that they had the flu is the probability of both things happening at the same time, probability of S and F, divided by the probability of getting the flu. Okay, so in this case it actually did help us to make a tree diagram because we need to figure out the probability of someone being a senior and having the flu, which was that first value that I found. So that's 0.0715. And the probability of getting the flu, so they actually didn't give that to us, right? We only have the probability of a senior getting the flu and the probability of a non-senior getting the flu. And so what you have to do at that point is you have to find the other probability of somebody having the flu, which is the general public. So I want to go down the third path, the one that I'm kind of redrawing over at this point. Okay, so 0.875 times 0.24, which is 0.21. So out of the entire population, general public and seniors, the probability of getting the flu is 0.21 plus 0.0175. So the probability of getting the flu, that's our denominator, plus 0.0175. So then our final answer is that simplified. So given that somebody had the flu, the probability of that person being a senior is 31%. And that would be your answer. All right, good luck.